This is a review for the third exam in Comp 360 Programming Languages at North Carolina A&T State University. The third exam will be Friday, April 24th from 2 o'clock to 3 o'clock. You must be logged into Blackboard during that time. It will cover all the materials since the last exam, which we will review in this lecture. The format of the exam will be similar to the second exam, although in this case you'll be able to go back and look at previous questions. Here are the topics and the websites that have further information on these topics. Of course, we'll be covering Haskell, which we spent a good deal of time on Haskell, so you expect a good deal of the material in the exam to be about Haskell. The MIT App Inventor, Prolog, and Java Streams for MapReduce.
If you haven't read the websites, now's the time to do it.
Websites explain the material. There are different groups of programming languages. There are the imperative languages, where the programmer specifies how the program should solve the problem. And then there are declarative languages, where the programmer specifies what is supposed to be solved and lets the program mostly figure out how to solve it. Functional languages, as the name implies, compute functions. Because you cannot change the value of a variable in a functional programming language, you have to use recursion instead of iteration. You certainly couldn't iterate until a variable had a value, because the variable always has the same value. There are what they call first-class functions, functions that take other functions as parameters, and you can return a function. These functions have no side effects and always return the same value given the same input. Here are some of the operators commonly used in Haskell. The ++ will concatenate two lists together. The colon concatenates an element and a list. Note the difference between concatenating lists and concatenating an element. You've got to keep the types correct. And the exclamation point will give you a specific element from a list. There are some very useful simple list functions. Head returns the element of the first list. Tail returns a list without that first element. So head and tail work together. Head gives you the first one, tail gives you the rest. Although note that head's an element, tail is a list. Similarly, but in the other direction, last returns the last element, and init returns everything but the last element. And of course, length returns the length of a list, and null is true if the list is empty.
The head is the head, the tail is everything else. Init is the beginning of the list, except for the last, which is the element at the end.
The sum function, as you expect, sums all the elements in a list. Of course, they have to be numerical values. Product multiplies them all together. And ELEM is often very useful. It tells you whether a given element is in the list. So let's try this. Write a Haskell function that reverses a string without using the built-in reverse function. Write it now and pause the video. Here's a possible solution. So my reverse function takes a string of characters and returns a string of characters. Okay, the input parameter, which I called rat, and then if the rat is length of 1, well, then we don't have to reverse it anymore. We're done. Otherwise, if we take and put the last element of the rat first, and then just reverse the rest of the rat, and that will reverse it one element at a time. List comprehensions are a method of creating a list from a given function along with the input set and a predicate determining if those values should be included. So in the example here, we have a list which is 0 to 5, and we pick from that list the value x, and then the output function is just x squared. And that returns all the squares of the numbers from 0 to 5. Ultimately, at the bottom, we've added a predicate such that the x squared is less than 50, and we're taking the input values from 0 to 10. And so you can see the values like 6 and 7 are included, but 8 squared is not there, nor is 9. Here's a simple list comprehensive question. Write a function that takes a constant and multiplies all the elements in the list and returns that list. Try that now. Here's the list comprehension that will do that. As you can see, we take a list and a number, and then for every element in that list, we multiply the element by the number. And as you can see for the examples, it provides the correct results. Here's another example. Imagine we want to go through a list and remove all the elements that are not uppercase characters, remove all the lowercase characters. So for all elements in the list, we take that character as long as it's not true that the element C is in the list of lowercase letters. So ELEM finds out if C is in the list. If C is in the list, it returns true, and then we not it, so it returns false. So we don't do it if it's in that list. And you can see in the examples, it takes out all the lowercase letters, leaving the spaces, special characters, and of course the capital letters. Haskell programs are strongly typed. That is, the type of the variables is very important. Haskell generally can infer the type of the variables, both the parameters and the return values. You can also specify the type to make it clear to Haskell what you want it to do. Here's the specification for the built-in tail function, which takes the list with everything except for the head. And so it takes a list of variables of type A and returns the list of variables of type A. We used the letter A to specify any type. Now, it could be a list of characters. It could be a list of letters. So A is whatever it is. But if the list is of type numbers to going in, then it'll be a list of type numbers coming out. If it's a list of type characters going in, it'll be a list of type characters coming out. You should note that tail is polymorphic. That is, it takes different types of input types and produces different results based on the input types. Here are some of the type classes that Haskell has. These are not individual types, but they are groups of types. In other words, EQ is for any type that supports comparisons. You can compare numbers, letters, but you can't compare functions. ORD is for types that can be ordered, things you can put into order. Letters and numbers can be put into order. And of course, nums are numbers, integrals are whole numbers. You can define the type of variable here using a class type. So we say that some square is going to take a number. It has a number A, and so it's going to have a list of numbers and it will return a number. And there in the definition, it just says if null dog, meaning if the list is empty, it returns 0. Otherwise, the head of dog times the head of dog, square the first number, and then recursively call the function passing it the tail of dog. You can split a string into parts by putting that in the parameter list. If you put the parameter list, but parentheses, variable colon variable, then that means the head and the tail. So in this example, cat is the head and dog is the tail. And so we no longer have to split those up in the method. You can just use cat as the head and dog as the tail. Here's an example of the sum squared method again. Same type definition, takes a list of numbers and returns a number. See the first example where if you're passing it an empty list, it returns 0, and because we don't have to have the if statement. By putting the empty list as the parameter, if you pass an empty list, then it will use that version of the function and take the result to be 0. In the second example, where if it's not empty, we could have a cat is the head and dog is the tail, and it will multiply cat times cat, which you don't have to take the head function anymore because they were split by putting the cat colon dog, and then just recursively call it on dog. Guards extend this such that you can have a function in the beginning of using the parameters, and then if that function is true, then it takes the definition of the function on the right. In this example, the functions on the right are quite simple. They're simply single letters, but they could be, of course, full Haskell functions. So this one just says if the calculation of 100 times the right divided by total is greater than 90, it's A. Otherwise, then if it's greater than 80, it's B, C, and the otherwise, which is the keyword otherwise, as flug means none of the previous statements were correct. You can make it a little bit easier to read by using the where clause at the end, where where calculates a value that is then used in the previous statements to calculate which one of the guards is going to be correct. So in other words, where calculates values used in the guards. Also, it's important in Haskell that all the vertical bars line up, and you should space over for spacing. Do not use a tab. Haskell doesn't like tabs. Also, the W and where should be spaced under the vertical bar. It's kind of picky about indentation.
Hope you didn't forget your Haskell.
If you did the homework, you should have no problem with the exam. Prolog is a logic language, and it allows you to space a bunch of axioms and then pose queries or goals, and Haskell will tell you whether it's true, and if it's true and you leave a variable, it will give you a list of values that you can use to complete that variable. In Prolog, you can specify a lowercase letter, and it's an atom, and atoms are just data. And so you can have variables have uppercase letters. So uppercase letters start a variable, lowercase letters start an atom. Variables can be changed, whereas atoms are constants. Functors are a relationship between values. They can be relationships between atoms, as we show in this example where Fred and Mary are atoms, or you can specify variables. In this example, there's nothing to the right of the functor, so that doesn't define it, but you might have further definition of a functor. Here's an example of things you might do in a particular order in the morning. You might eat your breakfast before you brush your teeth. You might dress before you eat breakfast. Not always, but you might. And then, of course, you have to get up in the morning before you eat breakfast. You have to get up before you make the bed, and so forth. And then there's the can-do functions at the bottom, which says, well, you can do X before Y if the before X before Y is true. You can also do X before Y if Z, a variable Z, can be done before Y, and you can do X before Z, so that will chain them together. So if you ask Prolog, can you do shower before breakfast, it will respond yes, because you can do a shower before you dress, and then you can dress before breakfast, so they chain together. If you ask it shower before make bed, it will respond no, even though it is, of course, possible that you do a shower before you make bed. There's nothing saying that can't be done, but because it can't prove it in that order, it will say no. MapReduce is a programming paradigm used in several systems, particularly Hadoop and with Java streams. It takes a stream of information and then kind of runs it through a pipeline. It starts with a source, so you have to have some sort of source for the stream. Some creation of data. Often in big data, you might be reading data from a database. And then there are intermediate operations that take that data and filter it or modify it. And then a terminal operation that consumes the data and generally creates a final result. Most of the popular Java data structures that hold groups of elements belong to the Java collection interface. And the Java collection interface implements the stream method that generates a stream from all the elements in that collection. You can also generate streams from input and output classes, such as buffer. Here's an example. We're taking an array and using it as a source. So we create the array of elements, and then we use the java.util.arrays class and call the static method stream, passing it the array, and it will create a stream out of that array values. So it'll pass 2, then 3, then 5, and so forth into the pipeline. The first method coming after that is map, and map will take whatever element it gets and adds 1 to it. And then the next step is filter. Filter will only allow those values where that number mod 3 is equal to 0. Now originally, none of the values, but we've already added 1 to them. So this is the number plus 1. And then we count how many of them occur at the end. So in this case, there are 4 because 2 plus 1 is 3, that's divisible by 3. 5 plus 1 is 6, is divisible by 3. 11 plus 1 is 12, is divisible by 3. And 17 plus 1 is 18, which is divisible by 3. So the answer of this will be 4. Okay. On the exam, there are some likely questions. You're likely to be asked to write Haskell functions. You also will have to specify the data types or the Haskell signature of the function. And there will be several questions asking what is displayed by programs. And the programs may be in Haskell, Prolog, MIT App Inventor, or data streams.
Oh, Dr. Williams has already written the exam, so these questions are really likely.
Be ready to answer questions like these on the exam. The third exam in Comp 360 is Friday, April 24th from 2 o'clock to 3 o'clock. You have 1 hour to do the exam. You must be logged into Blackboard during that time.